Hi everyone, it's James. This is homework 7, problem 1. An electron is accelerated through 1750 volts from rest and then enters a uniform 2.3 Tesla magnetic field. What's the maximum value of magnetic force this charge can experience, and what's the minimum value of magnetic force this charge can experience? Okay, so the force on a charged particle moving through a magnetic field is the charge times the velocity across the magnetic field, and the cross product has magnitude equal to the magnitude of the charge. Cross product has magnitude equal to magnitude of the first vector, which in this case is magnitude of charge times speed, times magnitude of the second vector, which in this case is the magnitude of the B field, times sine of the angle between them. So if you have QB and B, and theta is the angle between them. Okay, so the maximum value of this magnitude occurs when sine theta has its maximum value. Maximum value of sine theta is 1. So the maximum value of the force is magnitude of Q times the speed times the B field magnitude. This is an electron, so it has charge minus E, where E is the fundamental unit of charge. So the magnitude of the charge is E, which is 1.6 times 10 to the negative 19 coulombs, times the speed, which we want to find out from the voltage through which the charge is accelerated, times the B field, which is the 2.3 Tesla. Okay, so to find the speed, I note that the electron is accelerated through 1750 volts, meaning that it undergoes a change in potential energy equal to QV, or magnitude of that equal to the change in kinetic energy, which is going to be 1/2 mv squared, because it starts from rest. So the final kinetic energy is the change in kinetic energy. And from this, we can get the velocity that we need. So if I solve for v, multiply by 2 on both sides, divide by m, I get that v is 2 absolute value of q, absolute value of the voltage change, which actually I'll write as delta v, just to make clear that it's a change, and divide by m, and take the square root. And so we get that this is 2 times the fundamental unit of charge times the change in voltage, which is 1750 volts, divided by the mass of the electron, which is 9.1 times 10 to the negative 31 kilograms. And so you come out with a speed that is equal to 2.5 times 10 to the 7th meter per second. So if I plug that in up here, I get the charge times the speed times the B field, and that comes out to be 9.2 times 10 to the negative 12 newtons. And as I'm often remarking, when we get a small number of newtons or some other quantity, it's not necessarily a small amount of force. In this case, it's a very big amount of force. because it's acting on a very small mass. Note the mass of the electron goes like 10 to the negative 31 kilograms. So this force, which is a small number of newtons, corresponds to something like 10 to the 19 meter per second squared. So it's a big force for a small thing, resulting in a big acceleration. So that's the maximum value of the magnetic force. The minimum value is going to be the minimum value of QVB sine theta. And the minimum value of sine theta is 0. The minimum value of sine theta is -1, but we're talking about the magnitude here. So it's really, if I take the magnitude, it's the absolute value here. So the minimum value is going to correspond to sine theta equal to 0. So the minimum value is going to be 0. It's going to be absolute value of QVB times 0, which is 0. All right. And yeah, just as a final note, this change in potential energy was equal to change in kinetic energy. That's how we got the speed. And then we plugged that speed into the Lorentz force magnitude, QVB, to get the maximum value. And the minimum was just 0 because the minimum force corresponds to the particle going parallel or anti-parallel to the magnetic field. So if theta is 0 or 180 degrees, you get that the force is 0. All right, well, thank you for your time, and I hope this has been useful. See you again, hopefully.